Hello everyone. Welcome to the sixth or the seventh day of the lecture series. And today we are going to discuss about the discrete life annuities. So in this video, I'll explain the concepts of behind the two different kind of discrete life or the two different kind of annuities. And since it is discrete, that's why we need to deal with uh, different two types. So when we are advancing through the subtopics, I'll discuss the difference in and how to calculate these two quantities and go back and forth using these recursive formulas. So first one is the whole life annuity. So we saw these kind of similar things in the continuous case where we calculated for the whole life and the temporal life. We saw that we can use that YZ relation where we wanted to focus on the present value of the insurance benefit. And then if we knew that one, so then we could calculate the uh, present value of the annuity payment series. So that's how um, we deal with the whole life and the temporary life annuities in the continuous case. But for the other cases, I mentioned that we need to go with the first principles and the fundamentals to derive the present values. And we discuss about how they are interrelated. And we discuss about this annuity life or the discrete life annuity due. So this is the second type of annuity that we wanted to calculate. It is the annuity immediate. So as I mentioned, we already know how to calculate the uh, whole life discrete annuity and the temporal life annuity and the others deferred life and the certain life annuities in the discrete case. So it is the annuity due. Now we have a different topic which is called the annuity immediate. So the main difference in between the due and the immediate can be written like this. In most of the annuities, we started the payment from 0 and then we had 1, then the whole life case is go like this. And the payment started at this point with 1 and then 1 followed by a series of $1 or 1 rupee payment at the beginning of the year. So this was the sequence we followed for the annuity due. And in the immediate case, we have the same timeline, but the payment starts from 1. That means in here, the payment is made at the beginning of the year. In here, the payment is made at the end of the year. So that means the first payment comes after the first year end. And then we have the second payment and the third payment, so on. We will continuing to pay this series. So now we will see. So if I reduce this first payment from the annuity due present value, then since it is going to the infinity, I can get the present value of the annuity immediate because this one doesn't have any effect from the interest rate because it's made at the beginning of the year. So any payment made after the year has to be discounted back to the starting point. That means we don't have any payment in here. Still, as in the due, we have to discount all the payments at the beginning of the year 1, 2, and 3. So the same scenario, if I reduce this one from the present value, then the annuity due can be used to calculate the annuity immediate. So that's the concept. So since it is going to the infinity, we don't care about the endpoint. We approximate, we can say that when it goes to infinity, both values have the same present value. So because the present value of 1 is 1, which is made at time 0. The difference in the notation is for the annuity immediate, we don't have any hats or dots. So it's just AX. But we introduced 2 dots above the A to indicate whether this is an annuity due. We had a bar over the A to indicate it is a continuous annuity, and in the annuity due case we use 2 dots. It says it's an annuity due. So whenever we know that if it's an annuity due, we recognize it as a discrete series of payments. So then if we don't have any kind of hats or expressions over A, we know now that this is representing, so this represents an annuity immediate. So that's the 3 different nodes. So in the continuous case, we have this. If it is discrete, we have 2 circles. And in the annuity discrete, and we say that it is an annuity immediate if we don't have any expressions over there. So that's the difference, and the only difference. It's just one payment and we get this done. So that means it's easy to calculate the whole life annuity. Just subtract 1 from the immediate present value. But when it comes to the temporary life, then we have to deal with one more term, because in the due, so I'll refer the due as D. So we have a series of payment starting from 0 and goes up to the beginning of the nth year. So for the immediate, I'll denote it with I. The payment starts at the end of the first year, which is in this position, and the series ends at the end of the nth year. Now, we can see that if I get the present value of the due and if I get the present value of the immediate, then I can see there's an additional, which means there's a missing 1 in due if I want to convert this due into immediate, but there's an additional 1 at the beginning. So that means I have to do 2 things. From the present value of the annuity due of the temporal life annuity of n years, first I need to remove this additional 1. So that's why I subtracted 1. And then I have to add this missing, the present value of this missing 1. So then I get a similar payment, which is called, so similar payment scheme, which is corresponding to an annuity immediate. And I can get the present value without calculating it from the beginning. So if I know the annuity due of a temporal life annuity, then I remove the present value of the first payment and add the present value of the last payment. Then eventually I can convert the present value into the from annuity due to the annuity immediate. So that's the concept. And still we are using two dots for annuity due and just A for annuity immediate. So that's the two simple notation we need to keep in our mind. When it comes to the deferred life case, so deferred life means if you remember, starting from zero, we don't have any payments up to the nth year. Then at the beginning of the nth year, we have a payment there. Then that is the effect of the, if I get visualized like this, we can find the present value, the effect to the present value start from beginning of nth year. So we have one in here. Then continues to the infinity. And in the immediate case, same concept from 0 to nth year, we don't have any payment. And after n years, we have a payment. That means we have one additional payment at the beginning of n in the due. If I remove that present value, then eventually I get the deferred life annuity present value of an immediate scheme. That's why, so to remove this present value effect, so I'm removing it in here. So then it says if you have an annuity due for deferred life for n years, and if you remove the payment at the beginning of the present value of the payment at the beginning of the nth year from that present value of the annuity due, so you will get the corresponding annuity immediate value, present value. So that is given in here. So I'll circle the extra payment. So this is in whole life, this is the extra one. In the temporal life, this is the extra one in due. And this is the missing one. We need to focus. And in the deferred case, this is the extra one. So that's how we can build, or we can find the present value of an annuity due first. And then if I subtract these extra values and add the missing values into it, we will eventually get the corresponding annuity immediate present value for whole life, temporary life, and the deferred life annuities. So that's how it works. Now we can move into one example and see how we can apply these things in practice. So we are given the benefit present value of whole life insurance at age X as 0.28. And again, we have the benefit present value at age X plus 20. And then we have a term life. So in here, since we don't have here, so I need to include it in here. So this is, I'll write down the notation from the beginning. So this is equal to the present value of a pure endowment after 20 years. Now we have these two, and we need to calculate the present value for an annuity series starting from age X, but it's an annuity immediate. So this is the thing we need to find. X. And it's a temporary life annuity due for 20 years. So to find this, we know that if we could find the immediate value, then we can remove the unnecessary things and add the necessary things and convert it into annuity immediate. So from the YZ relation, we knew the annuity immediate from Y, the present value random variable of an annuity is equal to 1 minus the present value random variable of a benefit payment and the discount rate. So this is the YC relation. So if this holds, then the annuity due at age X for 20 years equal to 1 minus the present value of the benefit of the insurance, which is an endowment of 20 years. Then we can divide it by the discount rate. Now we know how to calculate the discount rate. It's I over 1 plus I. So we can directly take it from the scratch. It's 0.05 over 1.05. And for the present value of an annuity of the to find that annuity due, so we need the other component is the present value of the endowment benefit. So we can find, so we know that the PO endowment part is given, so we need to find the term life of 20 years present value. For that, we know we can use this relation. That means we can write down the present value of a whole life at X as the term life present value for X plus X to 20 more years plus present value of the PO endowment, and from there onwards we have the present value of a whole life. Now the age is X plus 20 and the PO endowment is given because we know that this is equal to in different notations we say the same thing. This is PO endowment. This is the present value of a $1 payment with 20 years ahead from X. So for this N, I can change it to 20. So that is the equation we need to substitute the values and get the corresponding term line. So we are given AX and all the other three components. So that means I can get the term life present value as 0.285 minus 0.25 times 0.4. So now we have the term life present value as 0.18. And then this component become the term life present value plus the present value of the PO endowment. And we know all the values on the right-hand side now. So you can directly write this one by substituting those two values. And then we have the other relation for the annuity immediate. Yeah, we will remove the extra present values. It is 1 now, which is the first payment at the beginning of the first year. And add the last payment present value, which is at the end of the nth year, which is now the 20th year. So we have given this one in here. And the final value (97) minus 1 plus 0.25. Final answer is 11.22. So now you can see we need to calculate only the annuity due so that we can convert it. But to do that, see, using the YZ relation, we don't need to do the summations or integrations. We can use the YZ relations for whole life, the deferred life, and the temporal life cases. Then we can convert it into immediate and the due as it is needed. So that's the story of annuity immediates and dues. Now we can quickly go through the empty life annuities, which is not like discussed mostly in this chapter, in this lecture, but I have included this one because it describes the theories a bit more. So if you are interested, you can follow it in the textbook. So in the benefit payments also, we mentioned that most of the time the benefit period was 1 year, but sometimes it was quarter, half a year, monthly, like that. And then we compounded the annual interest and using the monthly interest or the quarterly interest, half an year interest, and then calculated it as a different series of payments with the different time intervals with the same meaning. So in here, now since we are assuming that the annual payment is 1, so if we divide suppose we are dividing an year into equal 2 parts, and this goes on. If this is an life annuity, so starting from 0 and half a year, and then 1 year, and we have 1.5 years. Then at the beginning of the first half, we pay $0.50, and then we pay another $0.50, so that the total amount we contributed is equal to $1. So then M is equal to 2 here. So if you have like M different payments, that means you are dividing the year into equal M parts and you are paying 1 over M amount at the beginning of each mth interval. So that's the or the visualization of this payment scheme. And now we will see we have to discount back these 1 over m's. So that's why we have 1 over m times the discount factor. And then this is, so to make this payment, the person has to be alive, like in the annual case. So we need them to survive from the beginning age, or the age at the beginning, to the next payment date. So this says starting from X, surviving from X to 1 over M. And now we need to modify this equation a bit. So this is for the first case, from X to 1 over M. Then if they survive for next 2 years, it has to be X to 2 over M. Then for the third interval, X to 3 over M. That means the survival interval should be K over M. And the interest rate also compounded with that same gap. So this is K over M. So we need to modify that equation in the lecture note. So once you get that, you can calculate if you need the present value of the due. So you can calculate the present value of the second, or the second movement of the present value. Then you can move to calculate the variance of the present value. And if you want to convert the monthly payment annuity immediate, to calculate the immediate, it's same as the annual case. First, you should find the annuity due for monthly intervals. And now, since the first payment is 1 over M, so you should subtract 1 over M from the present value of the annuity due. And for the term life, again, in the annuity due, we have one payment at the beginning of the first year, so we need to subtract it. The amount or the value of the first payment is 1 over M. And at the end of the season, so in the annuity immediate, we need to pay 1 over M amount at the end of the nth year. So you need to add the present value of that 1 over M payment. And for the deferred case, previously it was $1 at the end of, or at the beginning of the nth year. Now you need to remove that. So subtract. But the payment value is 1 over M. So you need to remove the present value of the 1 over M payment at the beginning of the nth year interval. So that's how we convert these annuity dues into immediates in the monthly scales. So those are the things we need to discuss under this topic. So it's kind of an extra knowledge for you. Then, as in the benefit case, we can do relating different policies in different ways. That means even in the previous example we can relate uh, one term life benefit with a deferred whole life, or a whole life discounted back to the present life uh, with the whole life at age X. So that's the relation we used in this previous um, example. So like in here, so if you can visualize the series of payment, so you can see if I cut this payment by at some point, I can have a temporary life and a deferred whole life for the whole life. So this is the equation for continuous case. The continuous whole life means having a term life from X to N and having a deferred whole life after N. So this is a valid relation even for the benefit present value payment. And for the annuity immediate and the annuity due also have the same concept, but the notation differs from these expressions. So in here you need to use, if you need an annuity due and relate it with the temporary life and the deferred life, just stick into the notation and pick the correct numbers from the table or whatever the problem that we are dealing with. And if you are asked to find the annuity due, then you can use this relation with the benefit present values and find it. But if you want to find the annuity immediate, now you need to first write down the equation with the correct relation. The whole life is equal to temporary life plus the deferred life. And then convert those immediate values you have found into deferred values, or the due values into immediate values. So then you can find the whole life annuity immediate present value. So that is the concept in this first point. And also for the deferred case, I mentioned that. So deferring means we are starting the payments after the deferred period. So that means one can calculate the present value of the whole life annuity starting from that X plus N time point. And now it is away from N years from the present age. So what you have to do is discount it back to the present age. So this is the surviving probability and the discounting of the present value, which is v to the power n. And this is the present value of that annuity series, which start from X plus n. So now you can see, if you find this one using this equation, you can substitute it in here. That's same or similar in calculating the annuity due for the deferred whole life in the discrete case. Still, you can see this is the EXN, or the present value of the pure endowment case. So the pure endowment is valid in the benefit payments, but the present value in this form is valid for any cases. That's why we use it in the annuity payments as well. So you can find this one using the present value of the benefit of an whole life at age X plus N. Then you can convert it using the YC relation. Then multiplied by the present value of this annuity, or the pure endowment part, whether it can be annuity or it can be a benefit. Still, the pure endowment has the same calculation equation. So once you have this, you can have this annuity due for the deferred whole life. And to calculate it for the annuity immediate, still you have the same multiplicative factor, but you are multiplying with the present value of an annuity immediate starting from X plus N. That means since you know the due, you can convert it to immediate and use this equation. And when it comes to the empty case, the same concept. For the whole life, you have the temporary life and the deferred whole life. It's valid for the immediate and the due. And you can relate the deferred whole life with the same factor as the annual case, but now the present value of the annuity payments is compounded monthly intervals. So that's the only difference. So those are the things that we discussed up to these points, and I have summarized those equations there. So those are the equations actually we use in these calculations. And as I mentioned, we are not going to like more focus on these empty cases. It was included for your awareness. Now we can try this example in here. So we are given the continuous and the benefit payments for a whole life insurance at age 30 and a term life from age 30 to 40 and a pure endowment benefit present value at the age 40 when we are given the delta in here, not I. So delta is the log of 1 plus I. And we need to calculate these three for these four quantities, which are continuous annuities. And using the, since these are whole life and temporary life cases, we can use the YZ relation directly. So for the A, from the YZ relation, it says the whole life of, or the continuous whole life, or the present value of a whole life continuous annuity at age 30 is equal 1 minus the present value of a benefit of a whole life insurance, which is continuously paid. That means the benefit is paid at the moment of death. Then we need to divide it by delta because this is a continuous case. If this was a discrete case, so we use D instead of delta. And you can substitute these two values directly from the information. So it is equal to 20. And for part B, is temporary life annuity starting from age 30, but it's a continuous payment scheme, goes for 10 more years. That means ends at the age 40. So using the same YZ relation, we can write down the continuous endowment benefit of $1. And since it is continuous, we divide by delta. So to calculate the endowment benefit, we need to use the term life and the pure endowment, which is given in here. So the term life of a age, the benefit of a continuous term life benefit payment at age 30 and goes for next 10 years. And the pure endowment from age 30 for 10 more years. Divide by delta. And the value is 10. And the next one is deferred whole life continuous annuity. And so in this case, continuous means we assume that the payment is paid continuously throughout the year, but the total payment is equal to $1. So age is 30, but the payment start after 10 years. That is the beginning of the 40th year of the life. So in this case, so we don't need to like compute these things from beginning. From the relations, we can say, if I have a continuous whole life at age 30 and remove the temporary life part from that being a present value, so we get the deferred whole life case. So it is equal to 10 now because 20 minus 10. And for part D, it's a continuous whole life at 40. So to find this one, I can use this formula. So I'll write down the formula first. So I can say the continuous whole life at 30 is equal to temporary life (30) for 10 years and we can discount it back from age 40 where we calculate the present value of 40 first and then we discount it back from 40 to 30. So like since it is 40 to 30, so in this notation you should mention the present age, which is 30, and taking back 10. This says coming from 40 to 30 or coming 30 years from ahead to 30. 10 years ahead from 30. And we have these values. That means we can find the whole life at 40 and the whole life at 30 is 20. This is 10 divided by 0.7. Is equal to 14. So that is how we can use those things in calculations. So now we can discuss about the recursive formula. And in here, the recursion occurs for 1 year ahead. And we want to, like, if we want to calculate the future event present value after 1 year from now, we can use that one. Or if we know the present value of the present age, we can find what would have been the present value in the previous year. So we can go to the past. So it says we know that this is a continuous, or whether it is continuous or discrete. In annuity due and the continuous case, the payment starts from the beginning of the year. That means if I take one and consider the rest of the payment series, so it is equal to another annuity due starting from x plus 1. But it's in x plus 1 now. The same concept that we used to convert annuity due into annuity immediate. So at this point, we have the present value of an annuity due at age x. And at this point, we have the annuity due. So this is a due. Sorry about my writing pad. It gets some lags today. So we have this in here. And at this point, the age is x plus 1. So now we have one additional payment in here, and we need to get this present value back to here. So 1 is here, and taking the present value of that future ahead payment is B times the probability from surviving from X to one more year. So that's the equation. And you can apply that same thing for the temporary life. But now, since we are going 1 year ahead, that means in the temporary life of N, so we have already spent 1 year. That means we only have N minus 1 years to spend on that time. And for the age, at the beginning it was X, now it's X plus 1. And for the monthly case, now in the monthly case I mentioned that, so we distribute $1 or 1 rupee among the equal intervals of the year of M intervals. Now that's why the payment become 1 over M. And that means recursion occurs from the beginning to the next, the closest small interval, which is in this case, if it was monthly case, so if you have to start paying from the beginning of January, and the next immediate payment is at the beginning of February. So the amount is 1 over 12 because M is equal to 12 in the monthly case. So that means you are the recurrence formula starting from the January 1st and consider the present value at the February 1st, and you have to take it back to January 1st. And since it is 1 over mth interval, so that's why all these numbers are the payment is 1 over m, and the interval is 1 over m, and the surviving from x to 1 over m time. So that means to find this one, you need to use those fractional age assumptions. And sometimes in the like in the question or in real life, you need to assume the UDD or the uniform distribution depth or the constant force of mortality to calculate this fractional age assumption. So we know that if I recall these, so under UDD, we are modifying the survival probability, and in the constant force of mortality, so we are modifying the death probability. So we can use that in here and try to solve this example. So it says we need to prove this equation. So we can prove it by using the definition itself. So this says summation of payments from k equals 0 to infinity and we are taking this present value random variable in here, and the probability surviving from X to K years. Then when K equal to 0, the first payment become 1, and that means our summation become from K equal 1 to infinity, and the present value is v to the power K. The probability is same there. And now we have 1. Now we just need to change these form of the next term. You can take it like this. I take 1v and surviving probability from X to 1 year from this multiplication. Then the remaining part says v to the power K minus 1 and we have the probability from this X plus 1 to K minus 1. So if K star is K minus 1, when K is equal to 1, the K star is 0. That means I can write down this as V times Px and the definition says K star going from 0 to infinity and V to the power K star and P x plus 1 to K star. So this is the whole life annuity due at age x plus 1. So that is the proof. And now give a verbal interpretation of the recursive equation in this. So it says, so we have under the whole life annuity due starting from age x, we can say it like this. So we can say so this equation says one payment, which means $1 at the beginning, and then there's another annuity. So it says there's a guaranteed payment at age X. That means if you are at age X at the beginning of the year, you get immediately paid $1. So that is a certain payment. So instantaneously you get $1 when you're subscribing into this one. That means if you get a whole life annuity, there is a one payment which is certain at the point of buying it. And then the rest of the payments are subjected to the survival probability. That's why it say if you survive for the next year, then you can have another annuity series. So then in this equation, we say if you buy a whole life annuity due, then you get a certain payment at the beginning. And after that, if you like survives for one more year, so then you get uh, a chance to subscribe for another whole life annuity starting from age x plus 1. And even for that x plus 1, you are guaranteed for one more dollar at the beginning of that age. And if you survive another year, so then you get one more dollar and you are entitled to have another series of payment at age x plus 2. So that means depending on your survival state, at each year you will get $1. And if the death occurs in between these years, so then your payment schemes stops. So, but you get the payment at the beginning of the year. That means even in the death year, uh, the customer get a payment before the death. So that's how the annuity due works. Now we are given these information, the interest rate, uh, the probability of death from 30 to 31, and the annuity for whole life annuity due at age 30, and also the mortality rate identical except that um, from the mortality from 30 to 31, this should be 30 then, or either this should be 90. I think all these things are 30, so this should be 30. So the only difference is the first year survival probability or the death probability differs. Other than that, all the other probabilities are same. Now we are asked to calculate the new present value because of that change in the first year. So we can use the recursive formula directly now. So first, we apply these to the original scheme. That means 12.6 is equal to 1 plus, and the survival probability and the discount factor. That means the present value is 1 over 1.6 to minus 1. And from there onwards, we have, so first we need to multiply it by the survival probability. So I'll directly write down the survival probability in terms of the given notation. That means the survival probability is P30. P30 is equal to 1 minus Q30. Because since the Q30 is given, I'm directly writing down this equation in terms of Q30. And that is the probability we want to differ. So this equation says this. 31. And since we know all these other, even for this one, we know this is 0.05. Then we can find the value present value of the annuity due at age 31. So by simplifying this, you will get 31 as 12.94. And now the change is introduced in here. The new value, which is y, is equal to 1 plus minus 1. So in here it has to be plus 1. This is times equal to this times this new probability, which is now 0.02, and the annuity present value is 12.94. That means once we simplify it, it should be something equal to 10.768. So now we directly use this recursive formula. And now we are asked to calculate the annuity immediate value at age 30 for this whole life payment scheme, annuity scheme, using the updated death probability, which is 0.2. So this is not 0.02, it's 0.2. That means mortality has increased. Yeah, this is, I have introduced one more zero in here. Just give me a second. Okay, we are back now, and so it's directly ask us to calculate this probability, which is uh, use this probability and calculate this annuity immediate. So now we know that for the annuity immediate, it's just taking out that first payment from the annuity due at 30, and we can find that directly. It's 9.768. So now you can see how we can use these recursive formulas and how we can distinguish in between the annuity due and the annuity immediate. And then in one additional step, we can discuss how to relate these things in between the continuous, discrete, and the empty life annuities. So we discussed the similar pattern in the benefit payments as well. So the thing is, since we are using these four life annuities, so we can use the YZ relation directly. So for the continuous case, we know that the continuous annuity is taken by 1 minus the continuous benefit present value for whole life and divided by delta. And for empty case, still the annuity due but empty compounded. That means 1 minus the whole life x empty compounded benefit present value divided by the discount factor, which is compounded empty. And for DM, we can use this one. So that is how we relate the empty interval discount rate into the annual discount rate. And using the UDD, we knew that how to convert the discrete whole life present value into the continuous whole life present value. Just multiply by I and divide by delta. And to convert the discrete annual whole life present value into the empty whole life present value, we need to multiply that annual present value by I and divide it by the empty compounded interest rate. In the same way, to relate this into the continuous case, um, so the notation should be like I could see, yeah, this is annuity due. So this has to be a discrete one. So you just need to remove this hat from A. And in the same way, this is discrete to continuous, discrete to discrete in the empty manner. And now this is discrete. Therefore, hmm, it has to be discrete. Yeah, that means we need to change this like this is the continuous case because you know that to make the discrete annual benefit into a continuous benefit, we multiply by I and divide by delta. That means this is the continuous present value of a benefit for the whole life. So by dividing by subtracting from 1 and divided by delta gives us the continuous annuity whole life. And Now, when it's come monthly, so it should be a discrete because it's monthly. So then we have two dots in here. So monthly compound annuity due is taken by 1 minus. First, we have the annual discount rate or the annual present value of the benefit, and then multiply it by I and divide by the monthly compounded interest rate, and then divide by the monthly compounded discount rate. So the same equation, now it just got some complications. So this whole part gives us a bar x, and this whole part gives us a monthly compounded present value. And using the same UDD assumption, we can use this equation to get the continuous monthly compound annuity, whole life annuity, using the discrete annuity due and this alpha m and beta m equations. And these are given in the exam table. So you don't need to memorize these things. The formation is given in here for your knowledge, but it has the same formation. If you can see, the interest rate times the discount rate, the monthly interest rate times the monthly discount rate. And for beta, it's the annual minus the monthly interest rate and the monthly interest rate time the monthly discount rate. So that's the pattern. And this is for the continuous whole life. When m goes to the infinity, it becomes continuous, and the im become delta, dm become also delta. So in that case, we can relate this like this. So if you put continuous in here, we get a continuous value on the right hand. So if you put a continuous value to the right hand side, we should get a continuous value from the left hand side as well. So that means in here we have the monthly compounded continuous deferred annuity, and here we have the annual case. So in this place also we should get this annual value like this. And again, we get something like this. So this is the deferred whole life, and it's monthly compounded. And now this is the temporary life, which is again monthly compounded. So we have the temporary life in here for annual case. And now you can see for whole life, we don't have any multiplicative factor for B time, but for deferred whole life, we have this PO endowment part. And for term life, it's 1 minus the PO endowment part. So that is the pattern. So that is a way to calculate these empty compounded rates under the UD assumption for annuities. So these alphas, M and beta M, are functions of I and D, and IM and DM. So we can substitute the values and directly get these values. And even in the exam table, the formation is given and it's calculated for 0.05 interest rate. So if the interest rate is 0.05, you don't need to actually calculate this. There's a table. You can take these things from that table. And another equation to approximate this one is the Woolhouse formula with the three terms. So this is also mentioned in the exam equation sheet. So this is three-term case. If you are asked to calculate the two-term case, you just drop this last term and calculate the value using the first two terms. Even in here, so this is given for uh, whole life. If you want it to be term life or a temporary life, so then I'll write it to two terms. So then suppose you need this for empty compounded and a temporary life of n years. Then we have the annual temporary case. It's a due. That's why we have two dots. And this is for annual interest rate. Then we have m minus 1 multiplicative or the second term of the Woolhouse formula and multiplied by, like in here, since it's temporary, multiplied by 1 minus the PO endowment. We want it to be deferred one. We have the same term with the deferred probability or the present value for annual case and the same second term. But now the multiplicative factor is given in here, like in this case. So if you let this m to infinity, you get the continuous version. So that's how it works. So that's also an additional point. And now we can try this example quickly. So it says we have the death sign UDD, the probability of death from 60 to 61 is 0.3 and I is 0.06. We are given the continuous benefit present value at 61 and we need to calculate the uh, half a year compounded whole life annuity due at 60. So from the UDD assumption, since we have the UDD, so we can get so this is discrete. So we have two dots and we are using the same formation and alpha is 2 and alpha 2, m is 2 and alpha 2 is the function we need and the annual value is 60 annual case, and since it is whole life, we only have beta 2. And we can find I2 first, like this, m times 1 plus I, which is 1.06, and to half